Googled the phrase, yeah, because I basically know the monad, I know the monoid, and I know the functor. Yeah? How hard can it be? So I Googled it, and that was the result. So basically, just words, a little math, and no code. I'm a developer. I understand code, and that was a problem for me. So right now, I will try to explain this phrase to you using code, but still there will be some math. One more disclaimer. I'm deliberately ignoring all the laws from the category theory because I think that's boring. And okay, let's just start. So, monad, monoid, and the functor. You have already seen the functor and the monoid in the previous presentations. All of them are type classes. And okay, so what's the monad? The monad is a simple interface that have two methods. The unit, so we take the instance of a type A and put it inside of some type constructor f. Yeah, so we have this. Is it working? Whatever. Okay, so we take the instance of a value and put it inside some sort of the box, let's say it. And we have the bind method when we take the instance of this container for the type A and the function from A to container with B inside, and we return the container with B inside. So, yeah?
Scala?
Yes, this is Scala.
Can you explain the syntax?
Okay. Okay, so we are defining type, which is named monad, which have one type parameter, f. We say that this type parameter is type constructor, so it takes also one type parameter. And we define two methods. We first have one type parameter a and one value parameter value of type a, and the return type of this is f of a. Okay, and the same applies to the second one, so we have the function or method bind with two type parameters and with two value arguments. First one is of type f of a, and the second one is called f, and its type is function from a to f of b.
Okay, thank you very much.
I had a question as well.
Yeah.
It's been a long time since I've done Scala, but is the word unit not the same thing in Haskell as well? Like, is the empty tuple? Scala.
Yeah, basically, but it's just the name of the method here, so you can name the type the same, because there is a type called unit, but it's from the uppercase, and it's really don't crash.
Okay.
You can name methods whatever you want. So here's a monad example. We're doing this for the option type. You have already seen the maybe in the previous presentation, so this is similar. So if we want to put a value inside of the option, we just wrap it inside in the sum, and in Haskell I think it's just. Okay, and the bind, it's also like if we have the sum with a value inside, we just evaluate f, which is a function with that value. But it doesn't really matter. Let's go forward. We have the monoid. I have changed the names of the methods a little because they don't really, I don't really care. This was append and I don't remember. Empty, yeah, empty. So, but basically the type signatures is only thing that matters. So, the 0 is just some we return the instance of a f type, which is some 0 element, and we define the function combine, which takes two instances of type f and return the instance of type f as well. So, for example, we can have two instances of monoid for int. The first one is with addition, so the 0 element is 0 and the combine is addition. And the second instance is 0 is 1 and combine is multiplication. Yeah. basically the monoid and the monad, as I said, are type classes, so you can see how are they encoded in Scala.
So how does Scala know which one to use?
You have either this is not part of the language, so you have either passed them explicitly to the function as a function argument, or mark them as an implicit argument, and then you rely on the implicit resolution. This is some mechanism in Scala. Pretty complicated, so I won't go into details. And the last one, the functor, I think the simplest from them, we have still one type argument of type f, and one method which takes the instance of this f of a and the function and returns the f of b. It can be written differently, we will see that later. So this later we will see the definition that is more similar to the one we have seen in Haskell. So as well, the example of a functor for the option type. If we have a sum with a value, we just create the new sum with a result of this f function. Okay, so this was easy, right? Yeah?
Sorry, but you mentioned the monoid, but there is, you described it as just an interface, but there is an important contract here that is combined, associated.
Yeah. So this is what I was, disclaimer at the beginning that I'm ignoring laws.
Yeah,
So,
you know that, for example, in Scala, there is some problems, for example, Pituła, just because Pituła, there are two subtypes, math and list, Pituła subtype 4 and contingent.
yeah.
Exactly because someone missed that.
Yeah, I know. So basically, if I include the laws here, first of all, I have not done the formal proof for the laws, so what I told you may be false, but I rely on what the whole point of this presentation is to translate math into code. So
In code you just write a comment, here is a contract for this.
yeah, so there is a contract for all of this, yeah, not only for monoid. Okay, so right now you know probably as much as I knew when I was sitting here, and this is mostly the most important part of this phrase that I didn't know about, and it's basically towards one meaningful. And let's start. So what's the category? You can think of category as a set of objects. And okay, for all mathematicians here, I will simplify a lot, okay? It's a whole one big simplification, just because the presentation is originally targeted at developers. So just, if you think I'm lying, just treat it as feel like in a zoo. So you're just watching developers, monkeys, yeah, exactly. So you can think of category as a set of objects and some sort of transformation between them. They are called arrows. So for example, here we have the category of programming languages. We can have multiple categories. So we can have the category of good programming languages and the terrible programming languages. If there are any Go programmers here, I apologize, but it still applies. So how do we encode a category in Scala? Let's define a type with one type member here that defines a morphism. Okay, so we have some type with type member morphism that has two type arguments, f and g. And let's define the category of sets, which is what you know, and basically the category of types in programming language is I think it's equivalent to category of sets. So here the object in the category is type, and the arrow between the types is a function from one type to another. Yeah, is that clear for you? Right now it's mostly about the Scala syntax. So we have some type. Oh, I lost the pointer again. But anyway, let's just assume that it's just a function from f to g, so it can be, for example, a function from int to string and so on. We need one more thing, because we are talking about monoid in category, so we need not only the simple category but monoidal category as well. And to have that, we have to define two additional types. So the first one is monoidal product, which is a way to join two types together, two members of the category together, and the identity object, which is I don't remember the proper naming, but let's say neutral in terms of this monoidal product. Okay, so how does the category of sets looks like? We have our morphism, which is just a function. Our monoidal product is just a tuple. And our identity object is a unit. So the tuple, you are probably familiar with a tuples, yeah? So we have, for example, one int and one string, and so on. And if you put a unit and the unit in Scala is just a type that has exactly one value. So if you put some int and something that has exactly one value inside a tuple, it's equivalent to just this type, yeah? Because you can omit the unit there. Okay, and now we go to the monoid in category. So that's important part. We will be redefining the monoid we have seen at the beginning in terms of the category. So we have the category here that we specify that it has to be a monoidal category. And how does our two methods looks like? The 0 is a morphism we have defined, yeah, from identity object to the type parameter f. Okay, so in category of sets, this will be a function from unit to f. We'll see that in a second. Oh, yeah, you can see it in on the lower part of the screen. And the combine is a morphism from a monoidal product of f and f, and now it's missing here, but the result is f as well. So the implementation for category of sets looks really similar to what we have seen at the beginning. So if we go back, look closely. Here we have a function from unit to t, and the combine is a function from tuple of t and t into t. Okay, and if we go back here, we had a function that returns f. It can be named t as well. Sorry for that. And we had a function from two instances of f into f. So that's basically the same. Okay. And here's the example. So how looks the instance of an int monoid in this with this new definition? We define the 0 as just a function that returns 0, and the combine is just the function. We do a pattern matching against tuple here, so we are extracting the first element of the tuple, the second element of the tuple, and adding them. Yeah, just basically the same that we have defined before. Okay. So now you, yeah.
Come back 2 slides back. Yeah.
Okay.
So morphism is 0 is a morphism from identity object to f.
Yes.
From the other way around. But from f to identity object.
No. I think it's that way. So we have the morphism from unit into t.
So
There's only one object on this.
because like if you have a morphism from unit into natural numbers, is a morphism to a natural number. Yeah.
Yeah.
So there are many such morphisms, many possible zeros. So it looks like fishy to me, but I don't remember very well this theory, but
I think it's that way.
because if you put it other way around, like morphism from f, let's say from natural numbers into unit, there's only one such object.
But why you would like only have to have one such object? You can have multiple instances. multiple different, because you want at least.
I think that is right. I mean, the axioms, it's like when you have zero operation anything, you just get that one identity.
It's like,
Because you.
the thing is that like there is only 1 0 in numbers, and zeros
No,
are special unique element.
but the 0 is in scope of the combine. And you may want to define two different monoids. I have shown you before. The one with addition and the second one with multiplication. And in one, the 0 is 0, and in second, the output of 0 is 1. Because 1 is... Okay, so this... Okay, let's go a little forward. So that's another part that I didn't understand. So what's the endofunctor? I knew the functor that we have seen. So the functor is basically a function, let's simplify it, from one category into another. And these functions transform all of the elements of the category and all of the arrows of this category. And the endofunctor is just such a function, but the start and the end of the arrow is the same category. So it's basically the function from all of the elements of this category into this category back again, so to all of the elements of this category and arrows as well. Okay, so how this relates to the code? So we say that f is a functor because if we apply a type argument here, where there is an underscore, we create the new type. So we have a type constructor, let's say option, with one type argument. And we take then an int and wrap it inside the option, so we create the option of int, and that's type as well. Option is not a type, it's a type constructor, but option of int is type. Okay? So this is the mapping between objects of the category, because the objects are types, and this is a mapping for arrows, because arrows are just functions from A to B, and we transform each function from A to B into a new function from f of A to f of B. Okay? So that's an endofunctor. It's really hard. I'm not even sure that's possible to encode a generic functor. So what we name functor here is an endofunctor. But yeah.
We call that functor is just simplifying function. What's so special in this function, so we may call it functor?
Because it's a function between categories. It's not function between values, because typically when we say a function, we mean values.
I think functor is set of functions. So from that definition you had just before, this one, so we will get a set of functions.
Yeah.
Many elements as many types you apply.
Yeah. So basically, with f and this one method, we can transform each type into new type and each function into new function. So basically, that's a functor. At least this is how it's defined on the Wikipedia.
I have it, just to clarify. So, I mean, we know that a functor is essentially mapping something from A to B, but B could be different from the A, or it could be the same as the A, same type.
It can be different.
Right, but so an endofunctor, the distinction there is that the B is always the same type as the A.
Yeah, exactly.
Okay.
Yeah. And in this example, because we are talking about types, which is category of sets, we always transform types into types. So a functor is just a type constructor which can take one type and create the new type. Okay, so we need a little preparation because Scala has no kind polymorphism. By the way, who knows what's the kind in type theory. Okay, never mind. It's about the arity of type constructors. So if we have something with one type arguments, it's different than something that has no type arguments. So for example, int has no type arguments, the option has one type argument, and so on. So basically here we are defining the same what we had before, but not for simple types, but for type constructors. Okay, so the one thing that's a little verbose here is this product type, because for two type constructor we need a type constructor as well. So this out type is a type constructor with one type parameter. Okay, and here's a little preparation. We are defining few things to use them later. So we start with a simple case class, which is just a wrapper over a value. So ID for any type t takes a one value of type t and keep it as a member. Okay. The natural transformation it is just a something that for any given type A, okay, takes an instance of f of a. So for example, option of int, option of a, because we don't know what a is, and basically we can call it. Okay, let's say we have here the option of int, and what it produces is some other container of int. So for example, try or future or things like that, or the monoid, whatever. So the next thing you see here is just for convenience, so we don't have to write this long name natural transformation everywhere, so we'll use just this arrow. It's exactly the same. It's just type alias. And we have this compose, which for any given two type constructors, f and g, wraps one into another and produces some new type constructor. And let's see an example.
Excuse me.
Yeah?
What are those minus and plus signs?
I hope nobody will ask. So this is basically about the variance, covariance, contravariance, and I won't go into details on that. After the talk, I will publish the link to the slides and the code as well. Code on these slides probably does not compile, but I will give you the code that compiles. I have prepared that. I have not enough time to put this in the slides, but most of it is right. There are just some naming problems. Okay, so the examples. The example of the natural transformation from try to option. Do you know the try type? It's basically the same as an option, but instead of nothing, we have a wrapper over exception. So we either have a value or we have an exception. Okay? It's just a simple container as option or ID. So here we define this natural transformation from try to option that for any given type t, we take this instance of try and we return the option. This is built-in method on try, so implementation is not here, but you can trust me, it works like that. And x and y, just to see, on the right hand side of the equal operator we have exactly the same, so we can assume it's not a full proof, but let's assume it's what's on the left hand side is equal as well. So the compose of option and try is option of try. Okay? Basically the out here is needed because we define this type constructor as a type member. So we are accessing the type member out, but anyway, it's just a composition of these two type constructors. Okay, is that clear? Because there is a lot of Scala magic here, or maybe not magic, but a lot of Scala syntax that you're maybe not familiar with. Okay. Okay, and now this is our category of endofunctors. So the morphism is a natural transformation from some type constructor f to some type constructor G. Okay, it's not totally valid because we should have a proof that f and the g are type constructors, are functors, okay? But for simplicity, I omit that. And the monoidal product, which was a tuple, now is a composition of these functors. And an identity object, which is a functor as well, is in this ID type we have defined. I have not shown you the instance of functor for this ID, but you can construct this on your own. It's really, really simple. So basically the same what we have for category of sets. Now it's almost exactly the same, but we take different things here. So instead of a function, we have natural transformation. Instead of a tuple, we have a composition of type constructors. And instead of a unit, we have an ID type. Okay? And this is how we... ID type, we have defined this as here on top. So a simple wrapper over a single value of this type T. Okay, and monoid in category of endofunctors. So we already have seen how the monoid in category looks like. So we just put different category here. And what we get? The 0 is now a natural transformation from ID into given type constructor f. The combine is a natural transformation from the composition of two functors into this functor f. And we need a proof that f is a functor. Okay? Is that clear?
What is the double tilde arrow?
This is a type alias we have defined here. So this is just an alias for the natural transformation. Right. Okay? Just to have this a little less verbose. So yeah, just the natural transformation between different kinds of type constructors. Okay, and here is an example of an option monoid. So we can say that option is a monoid in category of endofunctors because we are able to define a natural transformation which takes an instance of ID and returns an instance of an option for any given type. So we just extract the value from ID and put it inside option. That's really not difficult. And the combine, so we say that option is a monoid here because we can define a combine. We can define a natural transformation from the composition of two options into an option of T. So we have an option of T. So box with a box inside with a something inside, for example, int or a cat. Okay? And we are able to make this box with a box inside with a cat inside into a box with a cat inside. So just remove one box. Okay? And this can be easily done with a flattened and built-in method. I may have implemented this here as well, but it will just complicate things. It depends, but let's say so. So we are just unwrapping it from one of the boxes. And we can say that option is a functor because we have already defined the instance of a functor for an option. Okay. So we are almost there. It's almost the end. So what does... There are just 3 letters left. Okay? Is a. So does any one of you have an idea how we are going to prove that the monad is a monoid in category of endofunctors? It won't be. Yeah?
Trust.
Nope. It's not going to be trust.
You said that you don't care about the law, so we won't.
It won't be a formal proof. But we want to transform this into code. So I want to transform the whole phrase into the code. So is a as well. So how can we prove something And once again, it's not a formal proof, so there are people who are doing a formal proofs with code. I'm not one of them. So I'm just doing trust me proofs, but still I trust the compiler and I trust the types. So as long as the code compiles, I think I'm right. That's how I see it.
Well, is A is going to either be an equal sign or a double colon?
Nope, but you're close.
Like we need to transform this. We programs to show equivalence. That we can transform every program that uses a monad into a program that uses this derived weird heavy thing.
Exactly. Exactly. That's what we're gonna do, but both ways. So from monoids to monads as well. And this is simple because this is just a function. For any given type constructor that we think is a monoid in category of endofunctors or a monad, whatever, we take an instance of one of the sides of the equation and return the second part of it. Okay? So we take the monoid in category of endofunctors and return a monad, and the other way around. And this is the first part. So not really long. Scala is a really nice language. It's very concise. Not as much as Haskell, but still it's concise enough. In Java I will need at least 3 slides just to show the first method. So.
But you get to scroll horizontally to show.
Yeah, okay, my mistake. But you see the signature here, just put it in your RAM. Okay, so the unit. So we want to wrap an instance of type A into instance of the monad. So we are using the monoid 0 method and take this value and put it inside the ID. So we had this natural transformation that for each ID can return the option. So here we just wrap something into ID, and with a monoid we get the option back, so our monad, whatever it is. And the bind, which is about the flattening of the things, we take the functor and this function from A to monad of B. I will call it like that. The M is a monad of B. And we take this function and run the map function on it. So what we get back? We get the, if we go back to the definition of a functor, okay, here we see that for any given function, it just wraps both of the sides into the type constructor, yes? So if we apply it here, okay, we get a function from M of A into M of F of M of B, okay? And then we give the instance here, so we call this mapped function with instance of F of M of A, and what we get back is basically M of B, and we combine it, which is a flattening, yeah? So we have the box with a box inside with a cat inside, and we removed one of the boxes, and it compiles and gives us just a monad of B. Okay? So this is the other way, from monad to monoids. It's a little bit more complicated, but still not that bad. Maybe I will scroll horizontally a little. Okay, I may have written too long lines. Okay, so let's start one by one. We want the natural transformation from ID into this monad. So, and the natural transformation take an instance of an ID and returns an instance of a monad. So basically this is just taking the value from an ID and running the unit method on it, because if we know that something is a monad, it has the unit method that takes the value and with the container. So this is what we do, and we have this our perfect natural transformation. Okay, so let's go with the combine. So here a natural transformation as well from this unflattened. So we have the container with a content, okay, and we want just a container with a content. So we are binding this instance M here with a function, with identity function. So basically identity function is just something that takes a value and returns exactly the same value. Okay, we use it just to make the code compile, so and everything works fine. And the last part is about the functor. So we have to define how do we know from if we know that something is a monad, we have to prove that it is a functor as well. So we will do it by using the we start with binding of a monad, and we are gonna take the f function, which gives us function from a to b, compose it with a monad unit, which will gives us a function from a into monad of b, and with it we can just get our functor here. So it's all. We have proven that monad is a monoid in category of endofunctors. We have defined all of the words that you have seen is definition as code. This code may not be fully readable, but still it's a code and it compiles. So the Scala compiler gives us some sort of guarantee that it's not that broken. So let's summarize. Yeah, I intentionally ignored all the laws because I think it's boring. So yeah, to have a full formal proof, you have to consider them. I have not done them, that's that. But if you find it interesting, just treat it as a homework. We have seen that category theory is not that scary. It's a math, but it is a math that can be translated directly into code. So I'm a developer, I can understand code, how complicated it is. So if you can, I may not be able to understand category theory, but I can translate it to code and then I will understand it. So that's my approach. We can see that we can prove, once again, something with a code in Scala. And we have seen that Scala type system is nice. So the last point is about that what we have seen here would be very hard to do in different languages. It is probably possible in Haskell, but for example in Java it won't be. I don't know, maybe it's possible, but it will be very hard because Java doesn't have the type members, for example. So this will be very, very hard. Okay, so if you are gonna any additional questions, that's the time. Yeah, you can find me on Twitter. You can find me on my website. There is also the whole of this written down as a blog post, so you can go there and read it, but whatever. Yeah, so that's it. If you got any questions or whatever.
I have a question, because I see that you've been using traits in Scala.
Yeah.
And my question is, what is the relation or the difference between traits in Scala and type classes in Haskell?
Basically the traits, because in Haskell type classes are built into the language. So there's part of the language. In Scala, we are just using traits which are completely not related to type classes, but are used to encode them. So in Scala, we are using traits to represent the type classes, but the traits are just, if you are from Java background, it's just interface on steroids. Or it's just an object-oriented class with multiple inheritance. So this is just definition of a type. it's not directly related to type classes. Yeah?
I think that type classes in Scala are encoded with implicits precisely.
Yeah.
Which come from Pascal to existing Pascal. But I think it is.
Yeah, probably. So basically, yeah, type classes in Scala are encoded with implicit instances of traits. Most of the time.
Now we know you're a wizard, but why is this useful for us?
Oh, well, I have told you that it's useful. It's completely not.
It's just funny to prove that the monad is a monoid and so on.
I just don't like things that I don't understand. And guy have shown me the sentence I didn't understand, so I have taken the code and...
But it's a good point that we often talk about monads and whatever construct from that theory, but we rarely explain why they prove helpful in our...
Okay, so about the usability, I think the last functional Tricity, there was a presentation about the algebraic patterns or something like that. So there, the guy was showing us the practical examples how we can use the monoid. So for example, we can use a monoid and a functor to implement map reduce, and that it relates, and things like that. So you can go to the meetup site, find the video and watch it, and then you'll see the useful examples. But I have not used any type of such code in production anytime, anywhere. So I don't claim it is useful.
Just to answer the question, I think we can say that monads can help in programming to generalize the idea to hide some details of those monads.
Yeah.
I mean, for example, when talking about the baby monad, we find a detail that's in object-oriented programming language you would check for those. And using a monad in, say, Scala or Haskell, you find this detail into the monad because it combines quite well. The same with lists either and other monads. So I'd say it's a property for some kind of types that helps you express some other concept.
So
using so much code.
yeah, so each of the different monads, they are very useful. For example, the option is very useful. Future, it's not a monad in a strict sense, but let's say so. Future, try, either, list, they are all very useful. The monoid and the functors, there are people who claim that they are useful as well, so let's just trust them. But this transition, I don't see any use for it, but doing so, we can understand Scala better. So because things I have used here, like for example type members, type constructors, and different elements of the Scala language as used in the libraries as well. So sometimes you want to understand how library works, because it's rarely ever you use this in production code, but sometimes you want to understand the library, and then you need to know how to use this language constructs. So, and this is just an exercise, like the code kata, let's say so.
Wait, are you saying that you don't use monoids or functors in production much?
Yeah, I don't. people outside Haskell do it like so, I think.
Don't you use option all the time?
Oh, but I mean type class instance for functor, for monoid. I use the. I use types which are monoids and functors and monads, but I don't use these type classes. So this is what I meant.
But you probably map on option all the time in Scala code.
Yes, I do,
So
but
you use the fact that option is functor.
not really, because Scala has no. When we define the map in Scala, there is no proof that this is a functor, because we are not talking about the laws. So without the laws, we can just assume it's like that, but it's not the proof. So Scala has nothing to do with the map function in Scala has nothing to do with the functor. Just the type signature, the method signature is the same. yeah, but there is also this last that has to be fulfilled to call something a functor.
So Scala has nothing like fmap that guarantees it must be a functor?
Nope. Probably. Maybe I just don't know something, yeah? So you just...
I'm not sure if you are able to prove that at all in Scala, because you do not have the notion of side effects in type systems. So if you are not able to forbid the side effects, I think you can do any rewrite rules. So.
Yeah, just the limitation. There are, for example, I think there is a language called COQ, that cock. Let's call it like that. And then it's not Turing complete, but there you can prove things. Yes, and Scala is Turing complete, and I think this makes it.
There's also iTrix, which is derivative of Pascal,
Yeah.
which takes some ideas from coq and tries to embed those proofs into the type system. And that's really interesting.
Yeah.
So coq is like a really cool tool to, I wouldn't even say it's cool. It is a language, but it's also a tool because the IDE of coq is like essential part of the system. And like, I remember using it once, it's such a great fun. So if there are people interested, I can give some talk about the coq and show some coding.
Yeah.
Because it's like the idea of giving proofs by programming is like really awesome, I think.
Yeah, I agree with that. So, because my main problem with math is that it's just some set of characters on a paper, and there's nothing that tells me if it's right or wrong and anything like that. And if we take programming language and computer into the equation, now that's getting more interesting because we can have some level of certainty that something is true or false. Yeah. Okay. Anything more? Thank you.